Hello everyone. So the next problem from the CSES problem set is array description. Uh, we have an array which can contain integers from 1 to m, and the absolute difference between the two adjacent values is at most 1. Okay. Given a description of array and some values may be unknown, your task is to count the number of arrays that match the description. Okay. So for example, we are given m as 5. So means we can use the values 1, 2, 3, 4, and 5. And this is the given array. 0 means we can replace it with any other number from 1 to 5. So we need to calculate the uh, number of arrays that can satisfy these conditions. So for this example, 2, 1, 2, 2, 2, 2, 2, 3, 2, because if you check any adjacent pair, the difference is at most 1. Let's see how can we solve this problem. Okay, so let's take the given array 2, 0, 2. We are allowed to use integers from 1 to 5. So this is the given range. Okay, so let's see it one by one, element wise. So if the value is already given, like the first element here is 2, so can we replace it with any other number? No, right? So it should be as it is. So how can we generalize this for all possible, like all the indexes? So we see that can we place here 1? The answer is no, means the number of ways is 0. Can we place it 2? Yes, because it is already present. Can we place 3 here? No. Similarly for 4 also, we cannot do it, and 5 also, we cannot do it. Okay, so now here comes the interesting part. Now the value is 0. So we can use here any integer from 1 to 5. So the bound is that the difference between two adjacent numbers should be at most 1. Right? So the number should be, if this is x, let's say we give it x, then the previous number can be x minus 1 or x plus 1. Now let's see if we place here 1. Okay. So now what we will check is if the previous element can be 1 minus 1, that is 0. Let me put it this way. If we place here 1, we can check the previous uh, number can be 0. No, zeros are not allowed because each element should have a number between 1 to m. So also here we can introduce this as we cannot place here 0, so the number of ways is 0. So if we place here 1, then the previous element can be 0, can be 1, or can be 2. So let's check if the previous element was 0, the number of ways was 0, right? We cannot place 0 at the previous index, so that contribution is 0. Can we place 1 at the previous index? No. We can see it, the number of ways is 0. Can we place 2 at here in the previous? Yes. So this is a way that we can use 1 here. Now, what if we use 2? So the previous element can be 1, 2, or 3. Right? These are the x minus 1, x, and x plus 1. So can we place 1 at the previous index? No. Can we place 2 at the previous index? Yes. Can we place 3? No. Now, if we use 3, we repeatedly check the uh, previous index for this given set of values, x minus 1, x plus 1. Can we place 2? Yes. Can we place 3? No. Okay. And similarly here, so we are checking, we are done with this one, right? Okay, so let's check for 4. For 4, the values will be 3, 4, and 5, right? So all of this is going to be 0, 0, 0. So I can directly place here 0. So the number of ways to place 3 here is total is 1. The total number of ways to place 2 here is 1. And also this is 1. Okay, now we know that we can place here 3 values. Now we come to this index. Now we have 2, right? So what we will check is, now it has 2, right? It already has 2. So the previous value can be 1, it can be 2, or it can be 3. So now what are the number of ways so that the previous value is 1? It is 1. What are the previous uh, ways to get to at the previous index? It is also 1. And for 3 it is also 1. So we have a total of 3 ways, and we have reached the last element of the array, and that means we are done. Now how can we do this is, how can we count the total number of pairs? So if we see the mapping for each element, for each I, we are mapping m values. We are constantly checking on, for each I, we are constantly checking each of the m values for each index. So for each I, we have m values. So now when we are at the last index, it will have all the ways that this array is satisfied. Like when we are at 2, we will have all the ways at various m's, right? So what we will do is, the final answer for our problem would be contained at the index n minus 1, because it will take care that all the conditions are satisfied and we are at the last index. So like here we had, like for the last index we went through, like you can also have other values, right? But all of them will be 0 because this element is already given. So this is 0. 2 has 3. This is 0. This is 0. So for the n minus 1 index, we can sum up all of these values that would be contained for all of these elements, and we can sum them, and that would be our answer. So as we are using the previous value repeatedly, we'll define a DP for each I. Like we have n elements, and it contains value from 0 to m. So we'll have, just to make sure we don't get out of bound, we'll have up to m plus 2, because when we are at index, when we are at value m, it will check at m minus 1, m, and m plus 1. So to handle this case, we will initialize the DP to m plus 2, and yeah, so the summation of DP of n minus 1 and I, from I will be from 0 to m, and yes, this will be our answer. Hope you understand how the thought process is. Now we'll look into the code. So we define an DP, we take in the array. Now for the first index, okay, so what if the first index is 0? So if the first index is 0, like it starts with 0 and has some elements. Now if it is 0, we have no previous element, right? So it has no constraints. So we can place here 1, 2, 3, 4, 5, all of these values. So we can initialize the DP for the first element, like all values are okay. So we can directly give all the values 1. Else, what we saw is, what we saw is the for the first element only this value gets 1 and all of the other are 0. So we only make that element 1. And now when we are after the first index, so if the value is 0, we'll check for the previous index this values, the neighboring values, value minus 1, value plus 1. And yes, and if the element is already given as the third index here, you can see that what we did was we just checked the values for 2 because it is already given. So we only consider 2 and its neighboring parts and we calculate it because all the elements are all the possible ways for others is 0. We can only have 2 here. So we will only check the neighbors for array of I. And yes, and finally at the last index we will have all the number of like all the possible ways. And yes, this will be our answer. We'll sum up all the ways and we'll output that. Hope the solution is clear. Thank you for watching.